Hey people, what's good? Mount Let the Hellfire. Welcome back for another video. Hope everybody's doing great. If you're new to the channel, welcome. This is part of a longer running communications and signals intelligence series for the prepared citizen, but I also do other breakout content on M110 SR25 gunsmithing, suppressor testing, AK gunsmithing, scope reviews, and otherwise. So I invite you to stick around for the rest of the video. And if you're going to click off, at least like the video on the way out. Thank you. I love you. Anyway, let's get right into it. Today, we're talking about RTL Power. It's a command line utility to interface with RTL-SDR software-defined radio dongles. And these are meant for broadband scanning. So unlike a GUI or graphical user interface based SDR software such as Cubic SDR, which is linked on the top right if you want to learn about that, or other software like SDR++, SDR Sharp, RTL Power is completely headless. You use it from a command line interface in a terminal, either over SSH, Telnet, on your Mac OS device, on a Linux device, or otherwise, Docker, Kubernetes, however you prefer to run these things, as long as you have access to a RTL SDR over USB. So before we get into it, and timestamps down below, as always, if you want to skip forward, I wanted to do a bit of a deep dive on the use cases for RTL Power, both from a communications intelligence and an electronics intelligence perspective. All right, so I'll try to get through these slides pretty quickly about leveraging RTL Power for ELINT and COMINT. So again, it's a command line utility, and it's meant for passive scans, and it supports only RTL SDRs, V3 or V4, and technically the old terminal armament SDR stick if you have one or have heard of it. It's meant for Mac OS and Linux. You can use it on Windows, but you'll either need to run it in a Docker container, use Windows Subsystem for Linux V2 with USB pass-through, or you could use VirtualBox or some other emulation software, virtualization software. Really, the long and short is it scans frequency ranges. It doesn't matter about the modulation. It's not a decoder. It's not a demodulator. It's not capturing raw IQ. And it just logs signal power per frequency bin. And a bin is a subsection of spectrum that you scan. And it writes it either to SSV, space separated value files, or to STD out, which is your standard output on the terminal, not the thing that you get from the prom queen. So the characteristics, again, it's using RTL SDRs. So at the minimum, expect 2.4 megahertz of stable bandwidth. Now, bins, they divide the frequency chunks. So let's say you're scanning 2.4 megahertz at a time into slices. So if you wanted to listen into like LMR, ham radios, repeaters, DMR P25, or other narrowband, typically you're looking at between 12.5 to 25 kilohertz. If you wanted to find some frequency hopping, spread spectrum stuff from, like mall or fast food radio intercom communications, or those funky Motorola radios that support 900 ISM, or you're looking for LoRa or some other IoT, you might want to use a much, much smaller slice like a kilohertz. Well, the signal power is averaged in that bin for an observation interval. And again, it's not a decoder, no IQs. If you wanted to do something like that, consider using Cubic SDR, SDR++, Angel that has an IQ mode. A bit more on bins. Again, they're small slices, small subsections of spectrum where you're going to measure it. So let's say you wanted to start at 928 megahertz. That's in the ISM band. There's certain LoRa devices that do support 928. And if you used 100 kilohertz bandwidth, that'll split it into 10 bins or 10 subsections. So 928, 0.000, 928.100, and so forth. Now, let's say you wanted to look at something like mirrors, or that's not 2 meter, but 136 is VHF voice comms. Now, if you thought it was narrowband, or it's narrowband, you use a 12.5 kilohertz bandwidth. So that'll spread it into 80 bins or 80 subsections, again, starting at 136 point triple aught, 136.0125, 136.0250. If you wanted better resolution, even though you're going to get slower scans, use small bins. And well, if you wanted just faster scans, or if you know that you're already using something like 100 kilohertz spread, then stick with the higher bin count. It really depends on what you're trying to do. I would say if you were just doing a regular old broadband kind of site survey just to figure out what's going on, 100 kilohertz, 50 kilohertz should be fine. That gives you a good balance of, figuring out regular voice comms and bursts, and even some types of radar versus trying to get into those like very, very tiny bin sizes, which your scan might run for a really long time, depending on the frequency range. Now, here's just some recommendations. Again, feel free to pause it or just use the timestamp if you want to come back to it. This is just some of the ones that I thought about. Wideband, you're fine between 50 and 100 kilohertz. If you're looking for like SSR, secondary surveillance radios down here at the bottom, like satellite beacons and telemetry, you might want to go a lot lower. HF, you are going to want to go a lot lower. You might want to go even higher if you're looking for, Wi-Fi, Bluetooth, even though this really isn't in scope for the RTL-SDR because it only goes up to 1.7 gigahertz. Now, there's plenty of voice comms there, and there's plenty of data comms, but anything else, you're going to need to build something like this on your own or use another tool. Maybe not with a hack RF, because while it does support 20 megahertz, it's not exactly precise. You're going to need something like a Blade, a Tiny SA, or otherwise, a higher end kind of mid-tier SDR to do that. Use cases, we already covered some of it, but again, it is continuous surveillance or reconnaissance if it's short-lived of the RF spectrum. You call it RF site survey, understanding your EME, your electromagnetic environment, however you want to call it. If you want to get more into the weeds doctrinally of like how ISRT works with information operations, how it works within intelligence, how to build intelligence products, understanding the intelligence cycle, check the video on the top right above, which is my deep dive into, doctrinal information operations and the intelligence cycle with some anecdotes spread throughout. Besides the surveillance part, you're going to be able to determine power of emitters irrespective of the modulation. So it doesn't matter if it's radar system, if it's a spread spectrum, upper sideband, lower sideband, narrowband FM, FM, AM, whatever. Besides that, you're going to actually want to save out that SSV file or pipe out the standard output into, cut, awk, rep, other Linux command line utilities to use. And you can do everything from making a chem, a known emitter mapping. So if you just keep doing these scans, let's say you start with mirrors, you start with GMRS, or you go for, the entire UHF2, UHF3 band, L band, whatever it is, over time, seeing the averages, you're going to see frequencies that are almost always active near you. It could be beacons, it could be repeaters. For COMINT targeting, so a subsection of that, let's say you've already exhausted open source intelligence SIGINT sources, right? So you use radioreference.com/db. You're looking for public safety, you're looking for colleges, for ham radio clubs, for docks, ports, airports, air parks, whatever it is. There's really nothing to listen to, either because it's all encrypted or you're not hearing anything. Using RTL power across those bandwidth could give you an idea of like, oh, wow, here's something above the noise floor. Let's boot up at Cubic SDR, SDR Sharp to try to listen to it. And then everything else is more data driven. Everything from exploratory data analysis, using DuckDB or writing and doing, just some basic things with SQL. Visualizing as a heat map. The guy who made RTL Power came out with a small little heat map utility that's fine, but in later videos, I'm going to show you how to write a better one, using pandas, polars, DuckDB to, hopefully build a command line tool for you guys. I'm actually working on a Rust version of RTL Power that'll have a ton of this SIGINT kind of processing and exploitation built into it, so you don't have to take the standard out and take the files and exploit the files. It'll all just be done for you. But my Rust skills are worse than my Python skills, and my Python skills are pretty bad, so hold fast on that one. So visualization, EDA, statistical anomaly detection, again, z-scoring, which are standard deviations above the mean. And since it's already doing signal averaging for you, that's a really good one to use it for. You could use ML-based, like I mentioned, isolation force, HMM, k-means. We'll get into that later. And you could also take all the data, and this is when you aggregate it and cleanse it and do all the proper data governance stuff to it over time. You could start to build sparse or dense vector embeddings, use qdrint, use LanceDB, or use pgvector, which is a plugin for a PostgreSQL database. And you could use that as part of a RAG workflow within an LLM. Later down the road, based on feedback. Moving on. So ELINT, or electronic intelligence, which is intel gleaned, just from RF sources that are non-communicative in nature. Now, theoretically, almost all sources of RF emissions are eventually used for communication or sharing data, but this means like non-voice comms, right? So not to say non-LMR, because there's other ways to go voice or text besides LMR, but you get what I mean. So it could be trying to find frequency hopping systems, getting those really, really small bin sizes and seeing how that moves across. IoT ICS sensors, obviously, LoRa is the big one. And don't worry about LoRa. We're going to be talking about Meshtastic and lower WAN in the future. Polling, bursting. There's certain types of radars under 1.7 gigahertz, which is the theoretical maximum that an RTL-SDR could support. And then certain types of long-range aerial surveillance uses, 500 to 350 megahertz as well. Russian Vorezhna, I believe the Pantsir S's secondary system, and the Buk M1, which is kind of an older air defense system. But the Russians run a lot of over the horizon stuff. So if you're in Maine or you're in like northern Canada, you could probably detect some of that stuff. And then also if you're near Southcom in like Miami, South Beach or whatever, and then transmitter power levels over time, a check on your emissions control, MCON, which is a principle of electronic protection within greater electronic warfare doctrine. Finding spurious emissions, maybe you go down to like a really, really small bin size and just power on your Anytones, power on your cheaper radios and see if they have spurious emissions. It could also be, you have an issue with your plug, an issue with the antenna or whatnot. That does happen. And then also identifying electronic attack, spoofing, jamming, beaconing. You're really not going to see a whole lot of that in the United States, but it does happen. For COMINT, there's really not a lot that you could do because there's nothing you could listen to, right? You need to use Cubic SDR Plus for that, whatever. I already spoke about that. But it's used for, targeting. And I know I said in the information operations video, we don't do targeting, but I mean targeting as far as like, let's go target a frequency in which to use our capabilities to match to our outcomes, right? So F3 AED is the acronym you typically hear for targeting operations in the military: find, fix, finish, analyze, exploit, disseminate. So for the F2 phase, find and fix, that's what you could use RTL power for. You could take a ton of different measurements as long as you're all synchronized and you have your parts per million error correction dialed in, and we'll get into what that means a little bit later. You could kind of do like really rudimentary, or I guess intermediate level. Rudimentary would just be using a Yagi and spinning in circles for direction finding. So this is one above it. To find and fix, busy bands in the LMR space, or again, radio direction finding. Use those high gain directionals, super fast sweeps, maybe bigger bin sizes, just to see what's going on. And then obviously, as long as you have the gain set up and you're more or less in the same area, again, you could do very rudimentary radio direction finding. Now, the RTL command line. So RTL_power is the tool. If you haven't seen my previous video on installing DragonOS on a Raspberry Pi 5, that's literally the fastest way to start with this. It's the most portable. You can bring them out to the field. You can power it off a battery bank. That's how I do it, and that's what we're going to do for the remainder of the series. Just write -H with RTL power in your command line to see the full commands, because the latest versions have some experimental features, but for the most part, this is what you need. So let's go one by one to what these mean. So -F is the frequency. It's spread into lower, upper, and bin size, which are delimited by a colon. So lower is the start frequency, and in this case, 902 megahertz. You could use shorthand. You don't have to write out the entire hertz and multiply it by a million. Just write 902M, right? Upper is the end frequency, and then the bin size, again, is that bandwidth in kilohertz. That's kind of it. If you just ran that without a file name or anything, it would just spit that out on the standard output and just continue to run through there. And remember, we're working off the assumption that you're on 2.4 megahertz splits, so it'll step through that in 2.4 megahertz. Next is -I, or integration time. So how often do you take a measurement? So this is saying how long do you scan within the 2.4 megahertz splits within your lower and upper size, and averaging the power. So the longer you run it, you might get some better averages. And again, that depends on your bin size. Or you could just run it super fast, omit this, or go like, -I1 or -I2 or something like that. -E is the overall duration. How long do you run this whole scan for? So like E-60 is for a minute. -E 3600 is for a full hour. You get the point. This is good for headless. Maybe there's a specific time of day that you want to run this for, so you use a cron job to automate this coming up in your sleep, and then it runs for an hour, and then the cron job runs every 6 hours, right? So there's different things that you could do just to make sure it doesn't run away and burn out your board or burn out the RTL-SDR, because those things do get hot when you have them running for a while. Dash G is the gain, amplification. This is fixed gain. And I typically keep mine on 30. That helps you be consistent and repeatable. And obviously, you're going to want to use the same antenna. Dash D is the device. So these are the actual device slots within your Raspberry Pi. So if you leave it out, it'll just use whatever index 0 is. So whatever the first device that it finds. So doing dash D space 0 is actually redundant. As part of your scripting, if you are going to script and automate this, you could use different devices, so you don't have to keep like swapping out the antennas. And again, this is important for doing this headless. Dash P is parts per million, so this is the frequency drift correction. So there's an internal oscillating crystal inside of the SDR, and it could actually drift. That could cause signal loss, or if you're doing further processing and exploiting, you could get some false positives within your statistical and ML-based anomaly detection workflows, or if you're trying to classify different types of signals based on their power, if you know where there's a source at. Now, I did put a calculation down there where, ppm will equal an observed offset in hertz divided by the tuned frequency in hertz times a million. So that'll give you your parts per million error correction. And the fastest way to do it, no matter where you are in the United States, 162.550 megahertz is the National Weather Service, or NOAA. You're going to be able to hear that, or, well, listen to it wherever you are. So take a reading off of that, maybe do like a smaller bin size, and for 5 seconds, 10 seconds. And if you see that you're off from the peak by however many hertz, that's how you could calculate that, right? Nice and easy. And then finally, the file name. If you don't put anything here, it prints the standard out. If you put a dash, it prints the standard out. And then if you actually specify something, so in this case, squiggly / lower sweep.csv, it'll write a CSV file called lower sweep to your home directory, which is what the little squiggly line, tilde, I forget what that is. I should know what that is. Who cares, right? And that's it. So I'm going to shut the hell up now and get VSCode up and running, and then we're going to do some of this live on the 900 ISM band. All right, folks, so here I am in VSCode. VSCode is an integrated development environment, also known as an IDE, created by Microsoft. There's also another version of this called Cursor if you wanted to work with generative AI tools, but that's neither here nor there. Just a quick Google search of VSCode, Victor, Sierra, code, right, together, and then you could download it for Mac, for Linux, for Windows. Now I'm using a specific extension called Remote Explorer. This will pretty much be automatically downloaded for you if you use Windows Subsystem for Linux v2 and you have VS Code downloaded already. It'll detect that it's there, and Remote Explorer gives you the ability to connect to Windows Subsystem Linux targets as well as remotes, so over SSH or tunnels. You see I have something else in here, an Amazon EC2 instance that I just use for bigger computing power to move stuff over. What I like about this is that, well, first off, this is a lot better, higher resolution, dark mode versus using PuTTY, which I did in the previous video where I installed DragonOS on the Raspberry Pi. That's up in the top right if you want to see that one. So you could interactively explore the home screen and whatnot. So I'm already at home, hence the little squiggly line, tilde, right? Or you could do LSA and see everything's there. And there's a bunch of hidden files and whatnot that you wouldn't see otherwise if you were using DragonOS with a screen or whatnot. So whatever. That's what that is. Now I have a cheat sheet up just to show you real quick what we're going to do. In the next video, we'll actually go over exploiting it. So if you wanted to, you can do RTL_power-H, and that gives you the little help menu with all of the various subcommands that we went over. A couple others that we did not, like -T-1 for a single shot, one and out. And then here's some of the experimental features, different types of windows, crop percentage, downsampling, things like that. Down the road, if anybody's interested, I'm more than happy to dive into these, but I don't really use them all that much, to be honest. And then it gives you the output columns, right? So you could see. So last night I did a scan across the 900 ISM band. So just to read it alongside here, right? This is the date. So yesterday, July 2nd, 2025, I ran this at night. This is local time, not UTC. So this is 8:36 Eastern Standard. The beginning, so this is 902 megahertz to 904 megahertz. Well, 904.6, because apparently I have 2.6 and not 2.4 megahertz of scan. And then the steps that it took, and then how many samples, bins, and then here's all the bins. And that's why I say this is not actually CSV, because if you tried to read this as CSV, one, there's no damn headers here. And two, if you try to read this as CSV, since these are all comma separated values, they would all get put into their own columns, which is stupid. Something else I wanted to show you, and let's close this sample out, is what happens if you can't start it. So you might get a USB clean interface error, especially if you have some other cron jobs running or whatnot and you wanted to use this headless. So I'll just copy and paste this command. And again, this scans from 915 to 917. So it's your typical LoRa boards at 10 kilohertz spacing with a gain set to 30. If you don't set this, it'll use the automatic gain control, which is going to skew your results. Collection interval of 5 seconds to average that out. And then it's only going to run for 60 seconds. So if I try to run this, you can see I got that error, USB claim interface error, failed to open up the RTL-SDR. So that's what happens if you hit like Control or Command V or Command C and just exit it out without it gracefully shutting down. It's going to stay claimed. And the easiest way to do that is use PSOX, and then you could grep out RTL. So this just shows you where in your system, what processes are currently using it. So this is the one that we used right now. This is a false positive. So obviously you see here the command line is the same up there. And the easiest way to do that is just kill -9. And then you would paste in that PID, then grep that again, and you see it's not running anymore. So that gets you your claim back. Now we're just going to run this and we're going to output the standard out because we don't have a file name specified. You could also use dash if you wanted to, like this. And then it'll give you some diagnostics when it begins. How many frequency hops? Obviously just one, because this is within the sampling rate. The dongle bandwidth at this time is only 2 megahertz. We're not downsampling. We're not cropping. There's the total amount of bins that we're going to get, 256, since we're doing 2 megahertz split into 10 kilohertz bandwidth slices. And then it's going to report every 5 seconds. It's using this device, whatnot. So you can see it's already outputting. And the reason that you want to do these broadband scans is, again, to figure out these noise floor are. So all these values over here, all 64 of these various bin values, is the actual average power within that. So you see they're mostly in the 30-40 range. So that's ostensibly our noise floor. Some stuff is a lot lower, some stuff is higher, but really my antenna is not sensitive enough. I'm just using like a 2 dBi gain Omni antenna from Newland, and you see it already exited because it was just for 60 seconds. So there's not really too much you could do with this. I mean, you could do kind of a Mark 1 eyeball, and you do hit Control F from in here. Let's see, like -5, nope, -4. See a lot of -40s. There's a -20, no, 2 dot whatever, right? So there's some of this that's a little bit above the noise floor. There is a way to figure out the exact frequency based on the number of samples and based on the actual bin. And then we'll do that in the next video when we actually process it. So that's all I had for you folks. Of course, the PowerPoint ended up being a lot longer than I wanted it to because I yap a lot, but I figured there isn't another deep dive on this and the reasons why you would use this. So hopefully you found this useful, and stick around for the next video in the series where we're actually going to exploit and process this data for part 3 of the intelligence cycle, because this is just part 2. This is collection right here. So congrats, you watched me do a SIGINT surveillance, boy. Anyway, that's all I had for you folks today. Make sure you subscribe to the channel if you want to see more of this. Check out the other videos in the catalog. Before you go, I'd appreciate if you could leave a like. Comment if you want to see more of this, less of this, have any specific questions, or you notice I did something wrong, want me to explain experimental stuff, want to talk about AI, whatever the hell it is. If you got family, spend time with them. This stuff is important to know, but it's not all that important. Don't let this stuff take your time, because it's a crazy-ass rabbit hole, and you'll end up like me, a freaking turbo optist talking about it on the internet. There's nothing more important than family, and if you want to exact positive change in the world, it starts with you, and it starts with your family, your community, it goes on from there. Lift more weights, eat more steaks. If you're going through some shit, you better talk to somebody, or I'll come find you and talk to you in person, goddammit. I'll catch you on the next one. Mount Lethe Hellfire.